So the other issue is that the Wi-Fi seems to have died all through the campus. I noticed this morning when I was setting up my learning catalytics. So I have it because I have a wire which goes in here, so I can see it okay. And I guess if you're maybe on your phone or something and you're using data, you could probably do learning catalytics, but I don't necessarily expect you to do that. So I do want to do them today and just at least run through them and chat about them. And if you have data, you could do them now, I guess, to get that done. If not, if you're relying on the Wi-Fi and it's not here, please just think about the thing, write it down, relax, don't worry about it, and then you can always do the asynchronous that I'll set up. I'll try to set it up right after class. Whatever I'm doing when I'm doing eating lunch, I guess I will, probably about 1 o'clock, I'll start the asynchronous section with the same exact questions, and then you'll have till tomorrow by 3 p.m. to just answer the 4 questions. You could answer them with whatever you wrote down, I guess, if you want. Does that sound okay? And I apologize for this Wi-Fi. But on the plus side, there's fewer radio waves going through our bodies right now. I guess it's... Yeah. Okay. All right, so this is I'm going to show you a funny video. There's no sound to it, but first we're going to see the car reference frame, which is not inertial. Then we're going to see the lab reference frame. So it's always a little fun to do it. Whoop. Hello. Oh, my computer's not going here. Here we go. So this is what you see in the car. Oh no! And here's the lab reference frame. The car accelerates, and okay. So, idea being there that when you're in the car reference frame, there are these fictitious forces. There's some sort of force that seems to be knocking your coffee towards the back of the car, but if you're in the lab reference frame, then really what you see is that, in fact, there's a forward force on the bottom of the cup, and then nothing on the top of it, so that it causes the whole thing to kind of fall. So another thing that can happen is that the car can slow down, and this is where these airbags come in. So if you're riding in a car that makes a sudden stop, then you might feel like you're thrown towards the front of the car. I don't know if that's my splitter again. That's the issue with this. Anyway. So there's really no force. It's the same thing with the mug. When you're in like a non-inertial frame and it's accelerating, then there's these fictitious forces that go in the opposite direction of your acceleration. But there really aren't such forces. Some books may describe the experience in terms of fictitious forces, but not this book. Since they're not real, they don't really help you. So at Kina, your author avoids fictitious forces altogether by doing the calculations in inertial reference frames. So you just go to the outside, and you'll see, actually, in this case, any external force on the passenger is backwards. Where's my notes? My notes are way over there. And I've also got my drink. So let's draw it out. Let's draw a force diagram for the guy in the car. So using the inertial reference frame of the Earth, this is how we draw the force diagram in this course. And note that there's no forward forces on the passenger. He's accelerating backwards. So the first thing I'm going to do actually is draw the little dashed line around the passenger is the system. Define the system as equals the passenger. And then there's the car, I guess, right? So if I want to draw a force diagram, let's go to blue. I'm going to draw a dot. And I might as well actually draw the force of the Earth on the passenger, which is the mass of the passenger times g, right? And then there's going to be, I guess, some upward force that cancels that out because he's not accelerating upwards, so maybe I call it normal or something. Maybe the car on the passenger, normal force or something of car. Maybe the seat, right, is pushing up on the passenger. And then there's this other force going backwards, giving him the acceleration, the force. Let's call it F, car on passenger. FC on P. So this FC on P is probably a normal force, something's pushing. Maybe it's the tension in the seatbelt or something. Anyway, it's something, i.e. the airbag pushing backwards. Car is slowing down. The forces on the passenger are opposite the velocity. Okay. So now I'm going to at least show a learning catalytics and talk through it, and maybe you will be able to see it. So I'm clicking on deliver. But we talked about it a little bit at the last day at the end of class. And did we bring a tennis ball? Is it in the bag? Yeah, no problem. Here it is. We talked about end of class. So there's F rest. That is this upward force I push on the tennis ball when it's at rest, of the hand on the tennis ball. I'm going to call it F rest or something like that. And then after it's thrown up and I catch it, there's like F catch or something like that of the hand. F catch. So how do those two compare? Now I can see how many people in the room have data. Looks like about 200 of you. Sorry again about this. So if you don't have Learning Catalytics open, maybe just, like say, write it down on a piece of paper, if you have a pen, and check with your neighbor. And then you're going to record those in the next 24 hours or so into the asynchronous course, please. You check your neighbor, please. Let me give a minute. Well, going once, going twice. Let's just take a look here at all you brave folks who are doing the Con Hall version. So you can see sort of illuminating great. So, and just to sort of, before I talk about the physics of it, you definitely, if you do this in Con Hall, you're at a disadvantage relative to the asynchronous folks, I guess, right? To get that extra like 20% for accuracy. So you can, I guess, anyone can always go and do the asynchronous afterwards and correct it if you want to. And I'll just take the higher of the two scores. But again, it's this you already got 80% for your participation, and you'll all get cut off at 2/3 when it comes to your marks at the end of the course. So I guess maybe I wasn't very clear in the wording of it, but while catching it, what I think is happening is you're slowing it down. Whoop. Let's see if I can catch. This is embarrassing. Okay, I can't catch. Catch. Okay. As I'm catching it, I think I'm slowing it down. Its velocity is downwards still while catching, I guess, is what I meant. But the acceleration is upwards. So I need an unbalanced force that's greater than the force of gravity on the tennis ball to give it that upward acceleration. Okay. So I wanted to talk a little bit more about Newton's third law, and this is from the textbook. This don't believe it. Well, you can check it. So here's an experiment. She shows 3 experiments, but I'll just show you the first 2, in which you take 2 carts on one of these tracks, and you put force probes on them. And you're going to be playing around with these sometimes in practicals as the force probes. They get hooked to the computer, and they record the force as a function of time in newtons. And so what these 2 red lines are showing is the force that's coming from the probe that's attached to cart 1 and the force that's coming from the probe that's attached to cart 2. And they're both plotted on the same graph versus time. And so experimentally, you can check that they're the same. And it doesn't matter if you were to change this is when the initial velocity is +2 for cart 1 and -2 for cart 2. If you were to change their velocities, maybe keep cart 1 at rest and have cart 2 only moving, again, Newton's third law still applies, but you get different values for these forces. They're less in this case because there's not as much of a change in velocity that has to happen there, less acceleration. But in every case, whatever reading which is coming off of the probe on one side is going to be the same as the one that comes on the other side. Members of a force pair are always equal in magnitude at any point in time. Measuring the force of 2 on 1 equals in magnitude to the force of 1 on 2. Okay, and we're going to use that sometimes in solving these problems. So, you want to do an example? We're kind of ending off. Whenever I end a chapter, we're sort of finishing chapter 3. I like to do a lot of little examples to show you what to expect kind of on the term test. So I've got a bunch of examples. Here's one. 3 blocks are being accelerated upwards at 3.2 meters per second squared by a force, F, applied to the bottom block as shown in the diagram. And this is not a force diagram, it's just sort of a sketch of the situation. It says the mass of the bottom block is 7 kilograms, the mass of the middle block is 14 kilograms, and the mass of the top block is 21 kilograms. So I guess M here is 7, and it's 2 times 7 and 3 times 7. And it says to find the magnitude of F, and it gives you the acceleration, 3.2. So what I'm going to do is I'm going to start off by defining the system as all 3 blocks. Define system equals all 3 blocks. And I might as well define plus y is up. So that means that a sub y is plus 3.2 meters per second squared. The mass of the system is 7 plus 14 plus 21, which I got 42 kilograms. And we need here the force. We'll call it m sub s or something. Okay, so we can do, in the simplifying diagram step, that's usually where I draw the force diagram. So what are the forces? So, and again, on the whole system, I think there's only 2, actually. You don't have to worry about all the internal forces between the blocks because I defined the system to be all of them. So it's going to be a part B, which will be harder. Okay, so there's F, and there's M system times G. That's it. Okay, so I'll just say internal forces do not go on a force diagram. They might be important if you were asked a different question. For example, if you were asked, what is the magnitude of the normal force that the top block exerts on the middle block? Well, then you'd have to do a different force diagram. We'll do that next. Okay, so just use here Newton's second law. A sub y is equal to the sum of the forces in the y direction divided by the mass of the system. So F is up, so you put it positive. Ms, the gravity force is negative, sorry, it's down, so you put it negative in your thing. Divide the whole thing by m sub s. Solve out for F. So I'm going to multiply just to get rid of that fraction. Ms times a sub y is equal to F minus ms times g. So F here is equal to ms times a sub y plus ms times g. Pull up the ms, I guess. A sub y plus g. So F is equal to 42 times 3.2 meters per second squared plus 9.8. So I got like 546 newtons. And maybe two significant figures, I could round it to F equals 550 newtons. Okay, rounded to two sig figs. Okay, so now we know F, which is nice. If part B was saying what is the magnitude of the normal force that the top block exerts on the middle block, I'm just going to sort of go to that. What we're going to do here, let's actually set 1 is the top. Let's just label them 1, 2, and 3. You can do this any way you want. 2 is middle, and 3 is bottom. I want to keep track of all these things. You are asked for what is the magnitude of the normal force that the top block exerts on the middle block. So that's 1 on 2. So you need absolute value of the normal force of 1 on 2. Okay. And I will just note, in case you need to use Newton's third law, by Newton's third law, I think this is the way I'm going to use this actually. N. Yeah. The normal force of 1 on 2 equals the normal force of 2 on 1. Okay, so we can find either of these. So what I'm going to do, I think it's just easier to define the system as being the top one and just look at the top one. So define system is block 1. Find normal force of 2 on 1, I think. That's what I'm going to do. So the diagram there is that there's the normal force of 2 on 1. That's what I'm going to try to find. So let's find this. And then there's a downward force on that system of m1 times g. And again, by Newton's second law, we know the acceleration. The forces in the f direction is equal to m1 times a sub y. That's going to be the normal force is the upward one of 2 on 1 minus m1 times g is equal to m1 times a sub y. And so n of 2 on 1 is equal to m1 times a y plus g. So, and this is going to be equal to the same magnitude as n1 on 2 by Newton's third law. So it's, the top block was 21 kilograms times 9.8 plus 3.2. I got 270 newtons. Sound good? So this is showing sort of two parts of a problem where I can, anytime I draw a force diagram, I have to pick an object. And I can pick that object to be one of the blocks, or I could put a dashed line around the whole system and say the object is the entire system, depending on what I'm trying to find. Okay. And I want to do another learning catalytics. And for this one, I'm worried about where the video is actually pointing. Are we going to be able to see the scale reading, you think? Okay. Maybe we'll have to pick it up and point it?
Yeah, so you want me to pick up
We can do that when we do it, right? Okay, so the question is, you've got, now actually we have two, not, how many newtons is one of the, I guess 5 newtons, right?
So
500 grams,
500 grams.
about 5 newtons.
Yeah.
In our case, we're going to have 2 5-newton weights. But anyways, we have 2 weights. Let's say for this one, if they're 100 newtons and they're hanging off the edge of the table on frictionless pulleys, and you measure on this scale, what are you going to get on the scale? And again, I think it might be delivering right now. 100 or 200? Or something else? You guys pick. And then we'll actually measure it. Do you think we would just pick up the video and move it?
Yep, I can move it.
I actually know the answer here. But I'm not going to tell you. We're going to check it. Even my wired internet seems to have died up here, so we're going total caveman here, but that's okay. Write it down. Okay, if you've committed to an answer, and I think learning catalytics has totally died, now we can just try to actually measure. I'm going to do aux plate, and we can try to see it. I want to show 2 things. One is, what is the reading right now? So you can see I've got, it's a 500 gram mass over here. So we would expect, that's 0.5 kilograms times 9.8, should be about 5 newtons, I think, of force to hold it up, and also 5 newtons of force to hold that up. So what do you think, Pius? Do you want to try to shine it on here? This is, well, it's reading grams, actually. And then the other thing I want to, can you see? It's right there, sort of between 400 and 600. It's reading 500 grams. So the answer then being 100 for that thing. So it's measuring the tension of either rope. The other thing I want to show is if I take this mass off altogether and just suspend one, like this, what do you think it's going to read? Lift it way up. The same thing. So it doesn't matter if it's suspending. So what I'm doing is I'm pulling upwards with that force of 5 newtons, and the string is pulling downwards with a string of 5 newtons. And what the spring is reading is just that tension, which is actually either way. It doesn't matter if it's horizontal or if it's vertical. The spring measures the tension, and the tension is transmitted all the way through this rope. If that sort of makes sense. Anyway, let's put it on the slide. Thank you so much, Pius. That's really cool. Meaning that the answer I was going for is B. So the tension is the same on both sides of the pulley. Okay, so this upward tension here, T is going to be 100 newtons to keep it stationary. And this tension right here is going to be 100 newtons, pulling it up like that. And that's what's going to be pulling here, and that's what's going to be pulling here. And so the scale reads the tension. It doesn't get doubled just because of Newton's third law, because that's always applying. So, all right. So we've been talking a lot about all these forces. What time is it? 11:37. So let's go through this big list, and we're going to fill in this chart here, which is going to give you 5 forces that come up a lot in this course. And we'll talk about, I'll give you an example of an object that's typical, that gives the force, object 1, object 2 that receives the force, maybe a symbol that your textbook tends to use at Kina, and then if there's an equation, I'll tell you the equation. So let's start with gravity, really easy one. So the object 1 is always the Earth in this case, and then object 2 is something like you, and it has some mass m. So, and there's an equation for it nicely. How you find it is, symbol is just F. She uses with E on O for object. Sort of a strange symbol to use, but you can use whatever symbol you like, as long as you're consistent. I don't care what symbol you use, but the equation is mg and the direction is down. So this is a force that emanates from the Earth somehow, and it acts on any object near the surface of the Earth, and G is 9.8 newtons per kilogram. Okay, next one is tension. So tension, I would say there's usually a rope pulling on an object. Does that make sense? The object's tied to the rope or something. Example being this mass right here. I have a string. I tie it to the mass, and then I can pull it around using that tension. So it's a pulling force, and it really depends on the situation. There's you can call it T, rope on O, and it could be 0 if the mass is sitting on the table. It could be, really high if the mass is like swinging around. It's just as needed. There's no equation for tension, unfortunately. That's okay. How about normal force? So you got a surface, acts on an object. Maybe the mass is sitting on the floor right there. So there's a normal force acting on it. You can use N, I guess. S on surface on object. And there's no equation. It's as needed. No equation for normal force. It's just whatever's needed to prevent it from falling through the surface. And if you don't believe me, you can imagine if a mass is sitting on a table, I could pull it up with the string, increasing the tension force until it's just touching the table, and reduce the normal force to almost 0. It's going to be 0 or more. Or I could stand on it, and then the normal force would be really high, right? It's as needed. So there's no equation for normal, unfortunately. Then there's static friction of a surface on an object. It's very similar to the normal force, but it's at a perpendicular angle. We call it F sub S, and then surface on object. So there's 2 S's there. First S stands for static friction. Second S stands for the surface on object. And there's no equation. This is as needed. Okay. Unfortunately, A lot of these things have no equations, which really screws you up. But luckily, kinetic friction does have an equation. It's just there's a little mu sub k times n. This is a chapter 4 kind of concept, but there's a good equation. So there's an equation for gravity. There's an equation for like sliding kinetic friction, but the rest of them are trickier. They're as needed. So you have to figure out what's going on and usually solve out Newton's law if you want to try to find them. Don't try to just plug in an equation because you're not going to find one. They're as needed. They could be 0 and often are. Okay, let's do some examples. Oh, I have another lovely learning catalytics. I don't know if my internet's back up here or if it's totally toast. It just spins and spins. Well, I'll show it to you anyways. And write it down. So maybe we could do a vote. In all three cases, the crate is in equilibrium, meaning no acceleration. They're going constant velocity. So either A, the crate is at rest, and she is pushing it with 100 newtons to the right. B, the crate is at rest, and she is pushing it 120 newtons to the right. And C is that the crate is moving along at 1 meters per second, and she is pushing it with 130 newtons. So what is the, which crate of these three situations is it experiencing the greatest magnitude of friction from the floor on the box? Maybe discuss. I will try to deliver, but I doubt I'm going to be able to do that. Spin. I'm going to do a vote, show of hands. Who votes for A? Who votes for B? Okay. Who votes for C? Oh, it seems to be sort of mostly B, with a smattering of C, sort of maybe 50-50. So I think it's just C. It's the idea here is that it doesn't matter what the velocity is. Acceleration equals 0. Acceleration equals 0. Acceleration equals 0. Don't try to look for an equation for static friction, which is what it is in these two cases, because there is no equation for static friction. It's always as needed, so it's 100 and 120. For this one, there is an equation for kinetic friction, but I don't need it, because again, I know that the velocity is 1 meter per second. It's not accelerating, so I can tell you right now, kinetic friction force is 130 newtons. Okay, and I can tell you just from looking at the force diagram, so we've got the normal force, the surface on the crate. We've got the mass of the crate times g. We've got a pushing force of the person on the crate, and we've got the friction force of the surface on the crate. Okay, and so I would just say if acceleration is 0, then Fs on crate equals the force of the pushing on crate. And also the normal force on the crate is equal to mg. So 130. Okay. All right. 70% answered B on this one as well. Okay. But never mind. using my hotspot on my phone now. It's getting pretty desperate. Want to do another example? So this is one kind of similar to what we didn't do last time. It's 2 blocks, and it's being pushed with an outside force of 20 newtons. So, and they're kind of touching each other, and they're maybe sliding along. It says actually a frictionless surface. So a 6 kilogram block is in contact with a 4 kilogram block on a horizontal frictionless surface, as shown in the figure. The 6 kilogram block is being pushed by this external force, 20 newtons. What is the magnitude of the force that the 4 kilogram block exerts on the 6 kilogram block? And there's a list here. It's one of these. So, and there's no friction. So maybe I'll write down that fact right there. And I'll say, okay, maybe I'll label them 1 and 2, and we'll say set plus x is to the right. This f is equal to plus 20, and we've got m1 is the 6 kilograms, and m2 is the 4 kilograms. So, and we need, you're asked for magnitude of the force of 2 on 1, but what I can do is just, by Newton's third law, that's also equal to force of 1 on 2. So just pick whichever one's easier to calculate and find that. F 2 on 1. These might all be normal forces, but I'm going to call them F's. That's okay. Find either one, and you're done. So, strategy. What I'm going to do is use, first of all, the system is equal to both, and solve for acceleration, a, sub x, I guess. And then use the system is equal to m2 and solve for the force on that, F1 on 2. So that's my strategy. First of all, let's do system equals both. So imagine the whole thing is 10 kilograms, and you're just looking at it. Well, then there's just going to be the normal force. There's going to be mg, m of the system, g. And then there's the only external force that's horizontal is the pushing force of 20 newtons. So I can say that the sum of the forces is equal to the mass of the system times a sub x. So a sub x, which is what we're trying to find here, is equal to that force divided by m1 plus m2. Okay. So now I have the acceleration, and I'm going to leave it in symbolic form. I guess I could just plug in numbers here, and you would know that it's 2, but let's just leave it like that for a minute. If the system now is equal to just m2, then, again, there's a different normal force, and m2 times g, but now I think there's only one force on it, and that is the force of 1 on 2 that you're trying to find. So again, sum of forces in the x direction is equal to the mass 2, because that's your new system, times a sub x. And that's equal to F of 1 on 2, which is what you're trying to find. So that's going to be equal to m2 times a. Let's write it out. Instead of typing in a, I'm going to just plug it in from up here. It's going to be F divided by n1 plus m2. So F1 on 2 equals F2 on 1 is equal to m2, which is 4, times 20 divided by 6 plus 4 equals 8. So let's see. Newtons, right? And time. Oh dear. Okay. Sure, having a lot of glitchiness. Let's do another one. And again, not quite sure if that's going to deliver, but Bob stands under a low concrete arch and presses upward on it with a force of 100 newtons. Can you imagine that? It's like a really low arch. If you're standing in a doorway, sometimes you can push up on the top of the door frame. That's what he's doing. So I guess imagine that he's on a scale or something. The question here is, what is the normal force of the ground on his feet? And normally the normal force would be 800 because that's Bob's weight, is 800 newtons, I think. But if he's now pushing upward on the door frame with 100 newtons, what does the scale read? Maybe we'll do a vote as well. But let's give you a minute to pair up and share, and then I'll also work it out. Okay. You know I'm going to interrupt you and see. So I'm going to use a little bit of process of elimination before we do the vote. I'm asking for the force of the ground on Bob's feet, so I think it has to be a pushing force. I think you can kind of rule out the downward forces there. So it's either 800, 900, or 700. So maybe we could, who votes that it's A? 800? Okay. What about, who votes that it's C, 900 newtons upward? Okay. A lot of hands. Who votes for D, 700? Okay, well, that's great. So, yeah, so the way I work that out is, let me just do it here. You've got, I kind of imagine that if he's pushing upward with 100, then there's also going to be, let's call Bob B and the arch A. I would say that the force of Bob on the arch is equal to 100 newtons, right? Up. So let's put a, and so that means that the force of the arch on Bob is equal to 100 newtons down. So if I define plus y is up or something, then I can do, let's draw a force diagram of Bob. System is Bob. So what are the forces? I'm going to put this one, the force of the arch on Bob. And then there's another one, which is the force of Earth on Bob, mass of Bob times Earth. And that's the 800. And then this is the force from the ground, force of the ground on Bob. That's what we're trying to find. So the sum of all the forces on Bob is equal to 0 because he's not accelerating. And you just sum them all up. I'm going to do it in the y direction. So the upward one is just Fg on Bob. And then you minus the Fa on Bob, the magnitude of it, and minus the 800, I guess. So solve it out. Fg on Bob is equal to 100 plus 800 plus 900 newtons. This is in the y direction, so it's an upward force of 900. So if you take a lot of high school physics, sometimes I see people telling me that the equation for normal force is mg, but that's not true. There is no equation for normal force or tension or static friction. Those are all self-adjusting forces that come as needed. They can be zero, or they could be as needed. And sometimes there's a maximum. I guess you could, if an elephant stood on that table, it might break the table, so the normal force would exceed its maximum or something, and it would break. Or a string might break if you pull it too much. But the tension is there from zero up to whatever its maximum is. And I got time for one more quick example, and then I think we'll be done for today. Two masses. This is another one of these term test style things. M1 and M2 are joined by a string. An upward pulling force of magnitude F is applied directly to M1. As a result, both blocks accelerate upwards with a magnitude of acceleration A. While accelerating, the tension in the string has a magnitude of T. What is the mass of M1? And it gives you a bunch of these other things. So I'm going to define, since I'm interested in M1, I'm going to define the system is equal to M1. And I'm also going to define plus Y is up to keep track of our forces, and draw what are the forces acting on M1 and see if this solves it for us. Well, there's F, up, there's tension, down, because there's a string below it, and there's also M1 times G, the force of gravity. So just try Newton's second law and see what happens here, which is that the acceleration in the y direction is the sum of all the forces in the y direction divided by the mass of the system, which in this case is M1. So I can write down all these forces. If they're up, I'm going to plus them. If they're down, I'm going to minus them because I defined plus y is up. So F is a plus, T is a minus, M1G is a minus. And then, don't forget to divide by the mass of the system. And then solve for M1, which I have to just do a little bit of algebra now. It's going to be M1 times AY is equal to F minus T minus M1G. Gather all the terms that have M1s on them on one side of the equation. I've got M1 times A sub Y plus G equals equal to F minus T. So M1 is equal to F minus T divided by A sub Y plus G. So I think they gave you numbers for all this thing. F was 36, T was 24, A sub Y was 2.2, and we know G, it's on our 8 sheet, it's 9.8. Okay, and so I think I got one. So it's this one, kg. But you may have to do this on the term test. You'll get a selection of answers and you kind of have to work through things. I recommend, as part of my strategy, I really like to keep things in symbolic form right to the end and then plug in my numbers at the end. The reason this is really helpful is because sometimes things you don't know cancel out because you have them on the top and the bottom, and you would never have figured it out if you had just plugged in numbers all along the way. Next time, we're going to go to 2D, 2 dimensions, okay? Two-dimensional force vectors, Newton's second law in 2D. Oh, boy.